If you want to know how to design airflow, I'm going to teach you all the information you need to know and give you all the engineering data that you'll need to design it really quickly right now. Don't get overwhelmed by all this information. Just go ahead, bookmark it so that way you can look at it later, but I'm going to just get right into it. You'll eventually end up with a drawing like this. You don't need to worry about the size of it just yet, all the ducts and everything. You're just looking for the longest run from the air conditioner and the return, including the return. Let's say over here in this top right corner. We extend the furthest away. We got to find the total effective length. If we was to straighten that whole run out, the turns, the bends, all that stuff, we would have to account for the turn because we lose pressure in it, right? We call that total effective length. We got to find a common denominator, and all those different fittings have different total effective lengths. Let me show you. See, like these plenums right here, they have different total effective lengths. These different branch connections, different total effective length. Different total effective lengths. We're going to add them all up so that way we get a total effective length for the whole duct system. This is a really important page right here. You can look at whatever type of duct fitting that you use. Most different 90s, duct boxes, etc. is on this page. You'll use this one. Depending on your area, it'll be different. Notice how the turning vanes affect the difference between the effective length. Without the turning vanes, it's 75. With those turning vanes, it's 10. That's the reason you see turning vanes in so many different units. Once we get all the total effective length, we add them together. The next thing we're going to do is check the blower performance table of whatever unit you're going to use. This is a blower performance table. It's actually in your installation manual. If you look right here on the bottom left, this is a 6024. It's a 5-ton, 24-inch wide cabinet. It's a constant torque. If you look up top with a dry coil with no filter, we'll add that in later. Don't stress it. And if you look over here, you'll see going up, it is capable of 1 inch of water column. As you can see, I already put it up here. Don't get lost in the sauce. It's simple. I worked it out for you right here. I went ahead and accounted for some of the engineering data of some of this common stuff that we use. A wet coil, dampers, a return stamp face grill, the most common stuff that we see all the time in the HVAC world. I used a MERV 8 filter. I got the engineering data for all this stuff. I'll show you in a minute. We account for a total pressure drop of 0.632, and our unit was capable of 1.0. Moving on down here, we got our equation, 0.368. When we subtracted 0.632 from the 1.0, that's what was left. That 100 will always be a constant. It won't ever change. We'll divide all that by 200, which is what our total was up here from all those duct fittings. We ended up with 0.184. That's what we'll design the entire duct system at. Return, supply, everything. This is Astropleat's filter. This goes over all the pressure drop of that filter at different rates. Here's the actual data right here. You can size it appropriately for your feet per minute. The reason I'm showing you this is because if you see, most filters are designed to operate at 300 feet per minute or 500. When you're sizing your return, I'm going to give you the maximum that you can do. These are what is recommended. So you can actually go smaller, but I'm showing you the maximum capability of this system. Now we're back at the blueprint. Now you can see we can go everything at 0.18 friction rate, and then you could turn your wheel and you could pick all the stuff that you want. Now in my example, I incorporate dampers because it gives us fine tuning capability. Sometimes you'll need more than a 7-inch, but not quite as much as an 8, and you can actually damper it down. There is a way to actually figure out exactly the exact percentage that you need to damper it down. The reason I tell everyone the maximum is because some people don't care about noise. So you can actually, this will tell you the smallest pipe that you can design this at, so that way if it's feeding a room, you know you're getting an amount of airflow. It's a cost-effective way to make your bids. A 7-inch pipe is cheaper than an 8-inch pipe. An 8-inch pipe is cheaper than a 12-inch pipe, etc., etc. It's cheaper to insulate. It's less stuff to carry around. You get the picture. If you're going to look at the velocity of the air, this is what they recommend for flexible duct. If you want to look at the velocity of metal pipes, this is it as well. Now you can play with all those numbers. Maybe you need a less restrictive filter. If you get below 0.1 on your friction rate, it's too low, and you need to change some of those things so that way you can get above 0.1. But what we're looking for is the maximum available friction rate that we can use. If you're still here, I really appreciate it. I'll also include the stamp face pressure drops as well. And thanks for watching. Like and follow. This is the stamp face information.